So they kept these strips on.
Yeah, they closed.
Keep those strips on now. We can see people.
They are more focused about the lighting.
Are you live?
Yeah, we are. Go ahead.
Okay. 11 o'clock, first Sunday of the morning means it's time for Chai and Wai at Prithvi Theatre. And this month is really special because we are part of the Prithvi Festival, which means that's why you see all these arrangements for recording and all the lighting and all this stuff. Of course, because it's a festival, also there's a play happening or being set up at the theatre. So we are here at Prithvi House. But it's a pleasure to be able to introduce Dr. Kalaivanan Nagarajan, who is Kalai, and he grew up in Erode, did his basic education there, then went to Chennai, Anna University Masters, did his PhD at IISER Trivandrum, and then for 5 years was at Strasbourg, where he was a postdoc. And so he trained as a chemist, and at some point decided to add some physics and light into it. And what he does is looks at chemistry with light, in as simple as what I understand is chemistry with light, and he's going to tell us more about that. And he's one of our youngest faculty members. He joined us rather recently, setting up his lab, and does some rather exciting stuff that he's going to tell us about today. So online audience, just remember that the only way we can get your questions, comments, etc. is on the chat. So please put your questions and comments in. We will monitor the chat on YouTube and let the speaker know what the questions are. So please do that. Meanwhile, Kalai, maybe should I go and start
Yes,
the
yes,
slide
please,
share?
please.
Okay,
Yes.
let me see if I can do it.
Yes,
I
yes.
will have to hit the Zoom.
Yeah.
So let me see if I can get Zoom.
So, am I audible?
Yeah.
Yes. So while Arnab doing the setting up ready, so I'd like to take this opportunity to thank TAF for outreach community for giving me this opportunity to come and speak to the public. Not like unlike we give the talks to that students or faculties at research institutes, it's really rare opportunity one can get to speak to the public. So where we can try to communicate what exactly science we are doing. So no. Okay. Yeah, please. Okay. Okay. So let them to set up. Can I get to know how many of you are from science background? Great. So how many are from the chemistry background? It's very rare to find people who are interested in chemistry, right? Yeah. So how many are from physics background? Okay. So I'll try to.
Your mic is online audience, so here you'll have to speak.
Yeah. I'm audible, right? Yes. Okay. So good morning, everyone. First of all, it's a great opportunity to be here. Thank you for everyone for being here on this rainy Sunday. It's like very rare to find people on Sunday, especially when it's raining, you want to be in your home. So thank you for being here. So the title of my talk is Magic in Between the Mirrors. Okay. If you are any one of you is thinking like I'm going to show some magic, sorry for disappointing you. It is nothing about magic, but what magicians are doing. What is a magic? Magic is nothing but, can you click once in that PowerPoint like for the slide?
Oh, it's not working.
No, once it has to be clicked. Okay, thank you. So what magicians do, they do something, they get something from nothing, or they transform one to other by non-conventional way. This is what magic, right? Magic is like kind of want to get it from nowhere, they have to bring something or they have to transform something to some other form. So that is not the magic what exactly I'm doing. But by the end of the talk, you will know what exactly the magic the title says. Okay. So before jumping into my research, I just want to say, who am I? Who am I? So I'm a kind of chemist. So I'm doing this. I'm practicing in chemistry research for last 15 years. So chemistry is a vast subject, right? You can see from very different, very vast area of science. But to classify myself, I'm an experimental chemist. So what an experimental chemist do? We are interested in making new molecules for different applications. We design molecules for different applications and we synthesize them. So once we synthesize, what do? We characterize. Is it the molecule what we wanted? Okay. Just after characterizing, we explore their properties. Okay. As clearly seen in this audience, chemistry is not a fond of subject, right? It's like chemistry on an average, chemistry is considered as a mystery subject, which is difficult to understand, right? But for myself, it was so different. I was so much in love with chemistry, so which made me to do research in this field of chemistry. Okay, so I'll tell you like what exactly we do. So I synthesize molecules and I use light to study about them. Okay, that's what mostly about spectroscopy we do. Okay, what is chemistry? So chemistry is about studying materials and their properties. Okay, but what exactly material? What is the meaning of material? Material is everything, okay, which has some mass and made up some space. Okay, in the figure you can see there are lots of objects. You can see butterflies, or you can see glass, you can see humans, plants, everything made up of material. Even here we have human beings, we have light, we have walls, we have carpets, everything is made up of material. So we all interested in material. So what is this material? We can see them. Okay. So there are something which we cannot see also. So the room is full of air molecules, right? We have oxygen, nitrogen, and we have dust, and we have virus, bacteria. Everything is made up of materials. Okay. So what is the basic unit of those materials? Can we say what they are made up of? What is the fundamental unit of a material? Atom. So we all know that everything is made up of atoms. Okay. What is an atom? Atom is something which people are trying to understand for a long time. Okay. In the very beginning, you can see during the early 19th century, atom was considered as a sphere. Okay. It has like, they are indivisible, but they are different in nature. That is what the understanding what they had during early 19 by John Dalton. Then the electrons were invented. So you know the J.J. Thomson's experiment, which he found the electron. Then he gave a model of electrons are like embedded in a nucleus framework. So that is a model we say like electrons are scattered spherically in a sphere ball. Then followed by the famous gold foil experiment, which was done by Rutherford, which clearly says the center of an atom is a positive core and surrounded by the electrons are roaming around. Okay, that is what the most understandable model of atom which was taught in schools. Okay, further, Niels Bohr told, no, the electrons are not simply roaming around, they are in an orbit around the nucleus. Okay, that is what the Niels Bohr model. This where people used to tell what is the orbit where the electrons are roaming in the electron. The most advanced model about atom we know is about the Schrodinger's model, which is like quantum model. Okay, quantum model says the electrons are there around the nucleus, but we cannot say clearly where they are. Okay, that is the most advanced quantum model we have. But just for our understanding, to keep it simple, we can have Niels Bohr model, which is like electrons are roaming around the nucleus at particular orbits. Okay, this is what about an atom we know. So we have an idea what is atom. Okay, but atom is the kind of, this is what I am saying. But how many atoms are there in the universe? So we have a different variety, right? We are like kind of, we need different varieties of people, but how many atoms are there which form this universe or matter everywhere, everything around us? So there are only 118 elements, okay, known till now, which made this universe completely. Okay, even among the 118, everything is not abundant. They are like, some are like man-made, some are like abundant, some are rare elements. Okay, so the elements are, so you can see this table, they are very cleverly organized. Okay, you can see the numbers and you can see the names of the elements. Okay, The number says how many electrons are there in the atom. Okay, the number of electrons and number of protons are same in a given atom. So the number says how many electrons or how many protons are there in the atom. Okay, you can see there some are different colors are there, right? It's like if you think about an atom, the orbit, whatever I showed in the beginning. So there are different kind of orbitals. Some are like spherical in nature, some are like different dumbbell shape, different shape of orbitals are there. Okay, the color says in which orbital the outer electron stays. Okay, if I have one electron, so it can be there no only one orbital. Okay, but if I have 3 electrons, 11 electrons, the electrons are arranged in a different orbitals. Okay, it's like kind of first orbital 2 electrons, then again 8 electrons. So there are different layers of electrons or arrangements are there. Okay, so the color says what is the outer orbital. Okay, here it is like s orbital, this is p orbital, here it is d orbital. There are different varieties of orbitals are there. So depending on where the electrons are in the orbital, the nucleus will have different attractive force. What is a nucleus? Nucleus is made up of protons. Okay, protons are positive in charge, the electrons are negative in charge. Okay, so the density of proton will have some positive attractive force towards the electron. It will pull the electron towards it. Okay, but if your electrons are so many number of electrons are there, but you have very small positive core, electrons will be freely roaming around. Okay, but if your positive is very strong, it is going to pull all the electrons towards it. Okay, that is a kind of atom. This is what exactly about an atom. So now if you start from the atom, but we are not coming across the atoms in our lives, right? Are we dealing with the atoms? We are not dealing with atoms. We are dealing with molecules. What are molecules? Molecules are made up of atoms. Okay, if I have two atoms coming together to form molecule. Okay, so the main element of our life is water. Okay, water consists of, what is the molecular formula? Water is H2O. So what it says, I have two hydrogen atoms and one oxygen atom combined together to form the water molecule, right? But how they form that water? It's like I have hydrogen atoms coming and oxygen atoms coming. How they form atoms? By sharing electrons. Okay, so now you see hydrogen having one electron here, oxygen are having how many? You see the atomic number is 8, so they should have 8 electrons. So I have 8 protons here and 2 electrons in the first circle and 6 electrons in the second circle. They are rotating around. So now what they do, they just share electrons to form some stable configuration. Okay, when they do, what happens? You see, this is the kind of structure you get. Okay, so here you can see this is hydrogen, this is other hydrogen. Hydrogen had 1 electron, hydrogen 1 electron, oxygen had 8 electrons. Now you see the outermost, the outer layer of electrons are shared between hydrogen and oxygen. Okay, when it does, so now hydrogen feels it has 2 electrons. This hydrogen feels I have 2 electrons. This oxygen has, it feels 8 electrons. Okay, it is a stable configuration. Okay, whenever you have an outer shell of 8 electrons, 2, 8 and all like stable configurations. So because of that particular configuration, you see water as a stable molecule. Okay, so now when you say water is a stable molecule, this is the configuration, this is the shape of a molecule. Now this is the only thing, not all the molecules around us made by this kind of atom hybridization to form molecules. Okay, starting from hydrogen, water, carbon dioxide, we exhale every time. So it's made up of 1 carbon and 2 oxygens, and you can glucose, or even whenever you take paracetamol medicine, this is the chemical structure, and we have the hemes which are there in the leaves. So like even for the water, I told you like 2 hydrogens and 1 oxygen is coming together. You think about the formation of this particular molecule. I have to bring all these atoms together to form this particular molecule, right? It's a very complex synthesis. That's why chemists most of the time spend their time in the lab to synthesize the molecules. Okay, all the drugs you get in the markets are synthesized by multiple steps. Okay, so now all these things are different basic units of our life which are made up of atoms, and this is the kind of molecules you see. Okay, so now if you start from a molecule, even this molecule we are not dealing. If you go for somewhere, you are not asking something like I need hydrogen dioxide, right? Hydrogen oxide, or you are not saying like I'm exhaling carbon dioxide. Okay, so now if you start from there, we always say it's a water. We are not saying H2O. or even you are not going to ask in the kitchen, you are not searching for sodium chloride. You always search for salt. Okay. So what is the difference between sodium chloride and salt or H2O and water? So these are all bulk. Okay. I am not dealing with a single sodium chloride molecule or single water molecule. I have n number of molecules condensed together to form this kind of water. Okay. Similarly, the rice what we eat is like this is the structure, and you see this is the macroscopically. So the diamond, it has only carbon atoms, nothing. The charcoal what you get in the stove and the diamond are having same elements. The only thing is like how they are organized or how they are arranged matters. Okay. So these are all different macroscopic structures of elements what we come across day-to-day life, and these are all chemical structures. Okay. So now if you go little deep into it, now again what I'm saying, the molecules are made up of atoms, materials are made up of molecules. Now water is forming from two hydrogen atoms and one oxygen atom to form this water molecule. Then it formed the glass of water. Okay. But if you closely go into the system and you see these water molecules are randomly orienting. Okay. So now if you take 18 gram of water, so if you take a 18 ml of water which contains Avogadro number of molecule. What is Avogadro number? This is the number of molecules available in a 1 mole. Okay, that is a unit people scientists use. So 18 gram of water contains 6 into 10 power 23 molecules. Okay, this many molecules you should have in a 18 gram of water. Okay, so now if you take water, the water, how do you taste? Is it tasty, salty, or sweet? No, the clean water is colorless, odorless, and tasteless. Okay. So now there is something called polar solvent. I will come to that. What is it? So it has a boiling point. Okay. What is a boiling point? Can you tell me what is boiling point? At which it starts to boil. Okay. It has a freezing point at which it starts to become solid. And it has some density and it has some pH, everything it has. So, but who determines all this property of water? How water gets all this property? Okay, why it should boil at 100 degree? Why it should freeze at 0 degree? But what is that fundamental? How we can get to that point? What is the fundamental for all this process? Okay, so now before going into that, I'll just go once more. We'll go back into the water molecule structure. You see, the water is made up of hydrogen and oxygen. So you remember I told you like something about the periodic table where the number of electrons are there and nucleus is there. So in hydrogen, we have one proton and one electron. Okay, here I have one proton and one electron. In oxygen, I have 8 protons and 8 electrons. Okay, if you see, it is a kind of sharing electron. So the both atoms share the electrons mutually. However, depending on the strength of atom to pull the electron, okay, it will have some asymmetry. It means the way oxygen pulls electron will be much higher when compared to the way how hydrogen is pulling the electron. So it means hydrogen gave the electron, oxygen also gave the electron, but oxygen tried to bring both of them towards it. Okay, that is what called electronegativity. Okay, so when I say electronegativity, there is a number. So hydrogen has electronegativity of 2.1, whereas oxygen has 3.5. It means the electrons are there in this space are mostly towards oxygen. Okay, because of that, there is something like dipole. Dipole means there is a charge separation. So now towards oxygen, I have more electrons. Toward hydrogen, I have more positive charge. Okay, it results in something called dipole moment. Okay, what is the dipole moment? Dipole moment says the electronic cloud. If you go and see that surface of electron, I have more electronic charge towards oxygen, whereas hydrogen has very minimum electronic charge. So this gives something like dipole moment, which is like a number which says how much charge are polarized. Okay, so now water is a polar solvent because it has a dipole moment. Any molecule, when it has a dipole moment, it is called polar. If it doesn't have that kind of polarization, that's called non-polar. Okay, you can see if you think about hydrogen. Okay, hydrogen is a molecule formed by between two hydrogen atoms. So when we say two hydrogen atoms, the ability of two hydrogen atoms to pull the electron is going to be same because both of them are same hydrogen atoms. So because of that one, there will be no dipole moment. Similarly for the oxygen. Oxygen also will not have any dipole moment because both elements are same. So because of that, they are called non-polar molecules where the dipole moment is zero. Okay. So now if we go little more further, now when I say the two, when I have one molecule, this is the configuration. When I have multiple molecules coming together, there will be some arrangement. There should be some attractive or repulsive force between the molecules. Now you see, as I told, oxygen has negative charge, hydrogen has a positive charge. When two molecules coming close, what happens? Positive will attract the negative. Positive and positive will repel each other. Okay, two negative charges will repel each other. Two positive charges will repel each other, but whereas positive and negative will attract each other. So now you see, when I have one water molecule, when the next water molecule comes, it will have attractive force to have positive and negatives are coming close. Okay, so when this particular configuration, I can say water has two bonds. Okay, they are called covalent bonds. Covalent bonds are formed by sharing the electron. Okay, this is what the water molecule. But there is a new non-covalent bond which is formed when two molecules are coming close. Okay, kind of one molecule comes, other molecules kind of sticking together. Whenever there is something sticking together, it should have some attractiveness. Otherwise, it will go away. When two elements are coming close, if there is a repulsion, they will move away. But whenever there is attractive force, when two atoms coming close, they will stay together because of the attractive force. So now the molecules are staying together only because of the hydrogen bond. Okay, this is something called hydrogen bond. So only because of the dipole moment which water molecule had, this kind of arrangements are possible. Okay, so now this is called non-covalent bond or intramolecular interaction, which makes the molecules to stay together like that. So we'll go little further. Now, if I consider about water, I have different states of water, right? We can go to ice or tap water, it's freely flowing, or once you boil it is coming as a steam. Okay, now
Before we get into this, there are a few questions on some basic
yeah,
bonding.
yeah,
So maybe this is a good time to take a break because others may have these questions as well. So one of the questions is that, just repeat the question for the online audience.
yes,
In case I'm not clear. If there is no fixed position of the electrons,
yeah,
right? You said the electron is actually the real picture is not quantum, but
yeah,
etc.
yeah.
Then how do we justify absorption of light, fluorescence, etc.? Because there is no fixed. Okay, that's one.
Okay.
Two, standard one, which is why does a negatively charged electron not fall into the nucleus, which is positively charged? Because
Okay.
you said positive and negative attract. So why doesn't an electron fall into the nucleus, but it
Okay.
is revolving around it?
Yeah.
And there is one more on Avogadro's number, but I'll come to it now.
Yeah. Okay. So the first question I will go to that even when the electrons are randomly oriented in the molecule, still how it is absorbing light. Okay. So based the model, whatever I showed now, it is like a very for a simple atom. Okay. But if you consider electrons, the randomness also there is some energy level gaps. So they are quantized. So when I say quantized, what is the meaning? The electrons are around the nucleus, but not at all the energy spacings. So there is an energy gap between the energy levels. So only because of those quantized energy levels, it can interact with the light and absorb it. So that's why the quantum nature of molecule was very important to understand the spectroscopy. So that is the first thing. And second thing is about why the electrons are not going into the nucleus. Yeah. So electrons are not, there is energy for the electron. It is not like once you remove all the energy, then it might happen. Okay. There is energy for the electron. Only because of those energy, it can continuously revolving around the nucleus. It's not falling into the nucleus. So the Avogadro number.
Yeah, so how was the Avogadro's number? How do they know that 1 mole has 6 into 10 to the 20?
Okay, so it's like kind of in from the schools we know that there is a unit, SI unit like mole. So they consider like kind of how many the depending on molecular weight. So depending on the molecular weight of the molecule and the density. So from there they used to find how many molecules. It's like kind of more into a mole number, Avogadro number. It's like it has its own definition. We should go back into that fundamentals. So it's like kind of school book definition why Avogadro number is 6.0 to 323. So I don't think we can go into the details of those. Any other thing?
No, that's it for now.
Yeah, okay. So we'll continue here. Now, if we consider water molecule, so water when it goes to, what is the difference between all these things? So I have ice, I have tap water, I have the boiling water. So if I consider what is the, how I can save them based on the temperature. Okay. So now I can play with the temperature to start from ice to the boiling water. Okay. So if I go below 0 degree or 273 Kelvin, it's ice. Okay. When I slowly heat the system, slowly, when I slowly heat ice, it can melt into water, and I continuously giving the temperature. When I continuously heating it, it can go to boiling state where it can it will boil off. It will be like kind of evaporate. Okay. But if I go into the structures, what happens to the molecular structures? So this is a molecular structure for the ice. So when I reduce the temperature, all the molecules will come close and they will be staying together. Okay. So you can see these are the covalent bonds. This is a hydrogen bond. So all the dotted lines are hydrogen bonds. The solid lines are covalent bonds. So now you can see, as I told earlier, the positive charge is towards the negative charge and it forms a kind of stable structure. But when I'm heating it, you can see the covalent bonds are still intact. Nothing happens to the covalent bond. But slowly the weak interactions or the dotted bonds are broken. Okay, slowly it is broken. It is no longer having a solid structure. Then if you continuously increase the temperature, you see all the water molecules are broken apart. So now I don't have any more the dotted lines. I don't have any weak interactions because the energy is so high to the system, they are kind of randomly oriented. So now they can escape as a single molecule. So that's what when you boil it, you don't see the water molecule, right? When you boil it, you don't see anything. It's like water is lost. So they are becoming like single water molecules at high temperatures. So now you see there is one more thing I can tell. Ice it floats on water. Correct, right? Why it is floating on water? Ice. How it is becoming less dense?
Arrangement increases in volume with the same number of molecules.
Yes. So now if you see, I have 6 water molecule. They are arranged in a way, but there is a empty space. So white space. This white space used to be like filled with air molecules. So only because of that one, ice can float on the water. Okay. Once you break any of the bond, it is no longer holding this particular structure and it can be freely flowing. That's what you see in the tap water. And when you continuously heat it, you completely break all the bonds and they are freely moving in the air. So this is about water molecule. Now, this is what we have to see. The covalent bonds are intact, but hydrogen bonds are broken. So now, this is the important thing what I am trying to come. This is the very fundamental of my topic. So now, if you see the spacing between the two water molecule, okay. So the covalent bond is somewhere close to 0.1 nanometer, but the spacing between the molecules is somewhere close to 0.2 nanometer. What is the meaning here? So now the space is not, what is there between these two in this space? So I can say I have oxygen molecule, oxygen atom, hydrogen atom, they are sharing the electron to form the bond, but here there is nothing like sharing. Okay, but there is some space between the two molecules. So what is the space in between these two molecules? Okay, that is a fundamental question we are asking. So now this space is something like a medium which communicate between these two molecules. Okay, there should be something to communicate. So now in other words, I have electron density here, I have electron density here, there is a space between them. What is there in that space? Okay, this is the fundamental question we ask. So now, before going further into that, now I mentioned like the matter is something which has mass and it is made up of atoms and molecules. So do you know anything which is made up of, not made up of atoms? Is there anything which is not made up of atoms? Vacuum, yes, correct. Vacuum is something which is not made up of atom. Okay, vacuum is a space. So that space, even you can see in the most of the vacuum tubes. So nothing is there inside. So that is vacuum. So there is nothing. But what about light? So the light what we see, that also doesn't have any atom. Okay, atom is light is a particle, so it's a wave particle nature behavior, which is as a light which doesn't have any atom. Okay, so these two systems are kind of intriguing, like kind of like atoms. So the light as well as vacuum doesn't have anything in it. Okay, what it is made up of. Okay, so similar to matter, we have some history of understanding about light. What is light made up of? Okay, so in the beginning, there was a very beginning, Aristotle told its essence of the particles are light or white light particles. They are particle in nature. Okay, so they are depending on mixing of the particles, you can get light and dark. That was the very beginning understanding. You see, from 3rd BC till 17th century, nothing was happening with about light. But during 17th century, Isaac Newton told, okay, light is comprised of colored particles. He told it, Aristotle told it's like kind of white light particles, but Isaac Newton told there are colored particles. He is saying everything about like bullet like particles. During 17th century, you remember like during our schools, you might have studied about the Huygens experiment, which says the diffraction of photons, where you understand like light is a wave. Okay, he told light is a wave like behavior. Then Maxwell came in 19th century. He told it's not like that symbol. It's not a particle or it's not a wave. He told it's like kind of dual behavior. It has an electromagnetic wave. So what is the meaning of electromagnetic wave? It has electric field and magnetic field are combined in the photon. So then the 20th century, Albert Einstein told, okay, it's made up of something called photon, which are like kind of quanta of energy. So this is about light. If we know about light, this is kind of electromagnetic radiation. So now for our understanding, this we come across every day. Electromagnetic radiation spectrum has different regions, which starting from radio wave to gamma waves. You know all the radio in our homes which are having antennas, so that use the radio wave frequencies. And if you think about the visible region where we can see, it has some region of light only we can see, but there are vast regions of spectrum for the light which we cannot see. Okay, but there are all the waves are called spectral regions. So they are into our regular life every day. You can see the microwave oven is using microwave. This is when you pass through these detectors in the IR frequency, you can see the image or your fluorescence or sometimes X-rays or gammas. These all they are in a part of our life, but we don't know exactly why they are, how they are working. But this is about light and vacuum. So now we will go into little more different directions. Now, if I speak, there should be a medium for the light to, so for the sound to transfer, right? So there should be some medium which can transport my sound. There should be some vibrations. Okay, but suddenly if I have a thought process, I put a vacuum box. So I am speaking from my source to the receiving end. I put a vacuum box. Do you think sound can be transferred? Okay, you cannot hear anything because there is no medium which is supporting the sound wave. Correct. So similarly, if I have something like light, okay, so light also propagating from source to detection. Now here also, if I put a vacuum box, do you think light can pass through? Light can pass through. How it is passing through? Because there should be some medium to transport that particular passage. Okay, so that is what the kind of questions we really ask. So now if you think about, even if you think about this room, if I remove all the air molecules, everything, light can pass through. So when a light pass through, what is light? Light is electromagnetic spectrum. It has electric field and magnetic field. So the vacuum should have something which can support the electromagnetic radiation to pass through. Okay, that is what called vacuum fluctuations. Okay, so vacuum fluctuations are nothing but the energy fluctuation in the vacuum space which can support the light waves to pass through. Okay, so little more further into the vacuum fluctuations, we all know that vacuum fluctuations are field in the universe. Okay, from the physics perspective, you can see, okay, yeah, so universe is filled with this kind of vacuum fluctuations. These fluctuations are the source of virtual particles. Okay, so we will not go into the debate of what is virtual particles, but they are the source of virtual photons. So these virtual photons or the fluctuations communicate the message between the molecules. Okay, so now which governs how they can interact. Okay, now this is for a simplistic picture to understand. I have water molecules. They are embedded in the vacuum fluctuations. Now, these vacuum fluctuations can communicate the message between these two particles. Okay, this is not only for this particular water, it is for everything. Whenever you think about a molecule, whenever think about matter, in the matter there are lots of molecules. The molecules are interacting through these vacuum fluctuations. Okay, so this is the understanding we have. Now the next question, this is what the question we ask in our lab: can we tune these fluctuations? Because now these fluctuations has, as I mentioned, vacuum fluctuation doesn't have any particular frequency. So they are like all the frequencies are possible. Now the question is like, is it possible to tune them? If I tune them, can I change the interaction between these two molecules? Okay, that is a question what you are asking. So now the answer is yes. If I have a open space, it's a kind of vacuum space. I have all the energy possible fluctuations. They will have all the energy levels. Okay, I have all the energy levels possible. Now, what I do, I bring two mirrors. Okay, what is it? Yes.
Question.
Yeah.
So, you say the electric field interact with the vacuum.
Yeah.
So, we know that the photons don't interact with each other. So, you don't think the photons interact with the vacuum flow and hence they should interact together? That's not
No, no, what I understand, I don't understand your question.
the photons independently interact
Yeah.
with each other.
Correct.
It appears that they might because of the vacuum fluctuation, but you know that they don't interact.
Okay, you mean two photons interaction you are saying.
Right.
No, no, here it's not about two photons. It's like kind of the fluctuation. So that's what I'm coming to the point. So now when I say this is the vacuum fluctuation energy, okay, so now this is a sink or reservoir which can accept the photon. Okay, it's like kind of like I have a photon, I'm just passing the photon to the medium. Through the medium, photon can pass through the next side. Okay, so now that's what the understanding. No, 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 I'm not saying that one. Again, we have to think about the Feynman's diagram. There are two photons has to interact through the vacuum fluctuation. Two photons cannot interact directly on them. So they have to interact through the fluctuations. Through vacuum fluctuations. Okay, so now this is, yeah. Okay, so now the question is, yeah.
Yeah, my question was that we are talking about light passing through vacuum.
Yeah.
Now, can we take the particle nature of light?
Yeah.
And say that the particle nature, since light can also be a particle, it breaks the presence of vacuum, because as soon as there is some particle in a vacuum, it's no longer a vacuum.
Yeah.
So it breaks the presence of vacuum and hence the light can pass through.
Okay, the question is like the particle nature of photon breaks.
Since it's a particle, it can just go through the vacuum as is.
No, no, yeah, I understand your question, but actually when you think about transport of photon, so when you think about particle, so what it is breaking?
If there is vacuum,
Yes,
and you put some particle inside the vacuum,
what particle?
any particle, just take any particle,
Yeah.
put it inside the vacuum.
Yeah,
Now it's no longer a vacuum because there
correct,
is something inside.
correct,
And that particular something, if it has a kinetic energy, it can
Yeah.
move around.
correct,
Photons have kinetic energy.
correct.
So can the particle nature of light
Yeah.
be the reason why it is moving through vacuum, instead of considering vacuum fluctuations and whatnot?
Yeah, we discuss this in the after the talk? Yeah, because we have to discuss little deeper. So the first question is about the two photons, how they can interact. The thing is like here what we are saying, the photons are not interacting directly. The photon, even when the photons are interacting, they should interact through the fluctuations. So that's what the Feynman diagram says. When any fundamental particles should interact through the fluctuations. Okay, it's not directly they can interact. Okay, so now if I think about the vacuum fluctuation in open space, I have all the energy levels possible. Okay, I don't have any particular fluctuation. But once I bring in mirrors, the mirrors, what they do, mirrors can reflect the electromagnetic radiation, or mirror can reflect the light. So once it reflects light, what happens if I give some wave inside some photon inside the mirror, what it will do? It will have some standing waves. So what is a standing wave? The standing wave will generate some only discrete levels of energy inside the mirrors that can support only the boundary conditions. What is the boundary condition? It can be half lambda or 1 lambda, 2/3 lambda, or it should be the multiples of lambdas. Only those energy levels will be allowed inside, all other things will be vanished. So in other words, I can say only these energy levels are possible in the inside the mirror. Okay, whereas in the open space, I have all the energy levels possible. So now the question is like, the only because of the reflection between the two mirrors, it has the standing wave. So then you generate these cavity modes. Now the frequency of, now I can see there are vacuum fluctuations in the open space. Now in the mirror, I can tune them. Okay, depending on the distance between the two mirrors. You see, I can tune the distance between the mirrors and change the wavelength. Okay, so now it depends on what it depends on the refractive index and length of the cavity, which can define what energy level should sustain inside. Okay, so now this is about inside the cavity. I will have only discrete energies available that I can tune. What energy should be available inside, I can tune. So now after tuning, now to what energy I have to tune it. Okay, so what I'm going to put some molecule inside. Okay, if I think about keeping a water molecule inside the cavity. So water has different energy levels. Okay, so it is very similar to the first question what it was asked, the spectroscopy. Though water has some all the water, it can just walk like this, water can move around, or water can rotate it around the axis, or it can do vibrations depending on oxygens and hydrogen bonds, or it can go to higher energy levels, it can jump. Okay, so these are all different possibilities for the water molecule once you give energy. If I give energy to the water molecule, water will consume the energy to do any of these process. Okay, either depending on if you give very lesser amount of energy, it can do faster rotations. If you give energy with corresponding to the vibration, it will do faster vibrations. Or if you give energy which can excite an electron, the water will get an electron and it will go to excited state. Okay, so these are all different transitions happen in the molecule. Okay, so now I can tune my cavity fluctuations or the cavity modes to any of these energy levels and tune my particular cavity. Okay, now I'll come to the next thing. So now if that is the case, I have these cavities. Now the standing waves are generated in the cavity. I have these cavity modes. They have particular energy levels. Now, if I think about molecules, you can think we can think about vibration. Now I have the cavity molecule inside the cavity, which is vibrating at a particular frequency. Okay. Now I can tune my cavity modes to match with this vibration. Okay, depending on my length between the two mirrors, I can tune the energy levels. You see, now I am just putting in for understanding, these energy levels are matching. It means the cavity modes are resonating with the molecular transitions. Once it happens, now molecule will have some different field. That's what I'm coming to the next thing. So now that is called, yeah.
So you are confining it along a particular
Yes.
dimension.
Yes.
The molecule has to be oriented along that dimension.
If it is oriented along the direction, you will have a stronger interaction. If it is not, then it will be weak. It's on an average, only 30% of the molecule will be in the confinement. Yeah. So now we have to come to the point like something called molecule cavity interaction. Okay, that is about cavity is there, cavity modes are there. I have the molecule inside. I have to think about the interaction. Before going to the cavity mode, there is something about light molecule interaction. Cavity modes are nothing but light. Molecule is kind of materials. So what is light matter interaction? Whenever you have a material or light, so the light when the light is impinge on the material, these are all the different events can happen. Okay, just light can transmit through the way the laser lights is passing through the air, or it can be absorbed. So it can be absorbed or it can emit. It can reflect. These things are happening today life. We come across all these events. These are all pictures of our daily life we are seeing. But these are all different events can happen when the molecule is interacting with the light. But these are all weak interactions. Like what is a weak interaction? When the light is falling on the material, it is getting absorbed and it releases the light. The light comes to the molecule, it gets excited and it releases the photon into the space. So there is no longer further interaction. So that's what it's saying. So now I have the photon coming in, the molecule go to excited state, and when it is come to ground state, it is released the photon and it's going to vacuum state. But in the cavity structure, when I have a cavity, so now I have a molecule go to excited state. When it comes to ground state, release the photon and goes to the cavity mirror, it will reflect back. Now photon again come to the molecule and it will be absorbed. It will go to excited state. It will release the photon. It will go back and forth. So now the molecule and light interaction will be stronger. That is called light matter strong coupling. There is a small video. You can just see about this particular thing.
To make a polariton, we need to add something to the light.
You have to increase
In
the
between the mirrors, we place a quantum well, which is only a few tens of atoms thick. It is
Okay, no
called a
issues.
well
So now you
because
can
it
just,
traps
I can
electrons in
explain
its
here.
plane so that they cannot escape.
No, no, no. Yeah. No. Yeah.
To
So the
make
sound
a
is not coming clear. I can tell you.
polariton, we
that
need to
these are
add
the two
something to the
mirrors.
light.
So when the mirrors
In
are
between
there,
the
I have a
mirrors,
molecule in
we
between. Okay,
place
the
a
molecule can be
quantum
any kind
well,
of system.
which
I
is
can
only
see
a
it's
few
like a quantum
tens of.
well, but this can be any molecule. So now the molecule contains electron and proton. So now they are in the ground state. So when I have a confined photon inside, now that photon can interact with this particular molecule. Whenever the molecule absorbs the light, the electron is excited and you have electrons rotating around the nucleus in a particular distance. There you have a hole and electron, that is called exciton. You generate some excited state. So when the electron is coming back to ground state, it is going to release the photon again. Okay, you can see now this is the electron rotating around. Now once that electron is coming back to ground state, it is going to release a photon. Yeah, now it comes to the ground state. Now it releases the photon outside. Again the photon is available. Now again the photon will come to the molecule, it will get excited, it will release the photon again. So now this process will happen continuously. Okay, so now when that happens continuously, you can just see that. Okay, so now it says continuous process. Now the electrons are excited, release the photon, photon comes into that. So now when they happen continuously, you don't differentiate between the light and molecule. So it's like kind of those two hybridize. So when those two hybridize, you have something called light matter hybrid states. Okay, whenever there is a hybridization between the two light and molecule, and you generate something called polaritonic states. I'll come to that little more. Okay, so yeah.
So electrons are present around an atom, not in a fixed orbit, though rather in a volume in which the probability differs.
Okay, go ahead.
So when an electron goes to an excited state and then comes back down, it does not have a fixed position from which it goes up and not a fixed position to which it comes down, right?
No, there is a fixed position. There is see the position. If I think about a circle, I have a radius for the particular circle, but in the radius my electrons are there. I cannot tell which exactly the point. So when I say electrons, we don't know what is the position of the electron. We know it is in the particular radius from the nucleus, but I don't know exactly what is in the xy direction. You understand? So now if I think about an atom, okay, I'll go back to the very beginning. I think that is the place I have the atom. It is necessary because that's very fundamental about an atom. Yeah, so you can see here, I have a nucleus. Okay, this is the first orbit. Okay, my electrons, I know the electrons are there in this orbit, but I don't know exactly in which place. See, now I have a static picture of, I have one electron here, one electron here, but it is not true. My two electrons are there, can be anywhere in this radius. Okay, but the radius is fixed.
It cannot, if this is say the circle in which it is going,
Yeah,
it cannot be somewhere here or somewhere here.
yeah, it cannot be here. See,
But if it is a cloud, then
Yeah.
it is supposed to be somewhere in that cloud, right?
No, that's what. See, actually, if I okay, they removed the board. Okay, now the radius, whatever is the blue line says. Okay, now I have a particular line, but in reality, that is not a particular line. It has some deviation from this particular line. There is a cloud-like thing in this around this blue line. Okay, but the next blue line is there, right? That is one more circle.
In that particular blue line cloud,
Yeah.
the cloud around the blue line,
Yes.
it can be anywhere.
Yes, yes,
So it is say plus something and minus
yes,
something.
yes.
And in that plus and minus, the energy
Yeah.
is different, slightly different.
It's slightly different. Yes, yes.
So when it gets excited or de-excited,
Yeah.
would the wavelength produced be different?
It will be different. It will be different because that is where you see the bands. Even in a molecule, that's why you have a bands. Whenever you see absorption, it is not a particular frequency it will absorb. It will have a lambda plus or minus del lambda it will absorb. Okay. So when you but if in a atomic picture, it is not the case. When I go to the molecular picture, it is correct. What you are saying is like I have some ambiguity in the energy level. It can have plus or minus thing. But when I go to atom, atomic transitions are very kind of very vertical lines. So now in atoms we know there is nothing like big interference. Okay. But when you go to the molecules, yes, you have a different molecular pictures. Then the interaction will be different. I have a cloud of electrons. So if I have a simple picture, I have a nucleus in the center. Okay. My first orbit is at the R1, 1 unit of R. I have a small round of cloud. Okay. Then I have R2, I have a round of cloud. R3, I have a round of cloud. But between 1 and 2, I don't have anything.
Maybe I said that you are right, it is fuzzy. But that fuzziness is, so that blue line or whatever is the average of
Yes.
where that fuzziness is. And that is, agreed it is fuzzy. The next guy is also
Fuzzy.
fuzzy somewhere else.
Yes.
So you can get something anywhere between here to anywhere between here to here.
Yes.
So that is what gives every transition some width. Because I could go from there to
Maximax.
or from here to there or whatever. Like, so this width to that width, but these are small compared to
Transition energy.
the spacings between them. So while they are fuzzy,
They're irrelevant to.
they are
Relevant, but
irrelevant because the widths are important.
Minuscule.
The
Yeah.
widths are smaller than the transition energy. So you will see the width. They're not exactly sharp lines. So they have some width. But the width is small enough that in this picture, even if you took it as a
Yeah.
one number, it's okay.
yeah,
Okay,
So-
of course, you will have to worry about the width in certain systems.
certain systems, yes. But not, see, I can show you. You can just see this particular thing. So this is a nucleus circle. Okay. So this is my first orbit. This is my second orbit. This is my third orbit. Okay. So this is a fuzzy. Okay. That fuzzy is there everywhere. So from this yellow, I can come to this yellow. Yes, it's a maximum energy. This yellow to this yellow medium. This yellow to this yellow, there will be minimum energy. That will be there. That gives the band of energy level absorption. But here I don't have any electrons. So that is a quantization. Okay. So now, yeah. When
To
that
make a
happens,
polarity
okay, this will come to that next thing. Okay, so whenever that happens, I have a molecular transitions, I have a optical mode. So when they are in resonance, when they undergo this energy exchange continuously, they have this hybridization happens when they generate something called light matter hybrid states. They are called polaritonic states. So when these kind of states are available in the molecule, what happens to the molecule? That is what the whole research field is about. Okay, so whenever that happens, I can have this particular energy spacing that depends on how strongly they couple. So once I have that kind of couple, I have this kind of new states. So now, yeah, so how do I can see that? How I can see in my experiment? Okay, so now if I do like kind of, if I have a molecule, like whatever I explained, there is a transition when the light is absorbed by the molecule. I have this particular energy level being absorbed. Okay, I have a cavity mode which is in the same place. These are, you see, those two are resonating. So whenever my molecular energy and my cavity energy is on resonance, what happens? They undergo this hybridization and I have a new energy states possible that can be seen by the split energy levels. So now this is an experimental observation where I can see this is from molecule where I don't have any cavity. Here I have cavity but I don't have any molecule. When those two are there intact, so when the molecules are injected into the cavity, I can see this kind of split peaks. So these peaks are characterization of this particular strong coupling, or this is a characterization where it says, yes, I have a new states are generated into the molecule. When you have this kind of states, what happens to the molecule. That is a field we are working in the lab. So that field is kind of pretty new. It started kind of 10-15 years back. So now we can see there are various properties have been studied under this particular constraint, and people reported like we can modify many properties when compared to the conventional thing. So if you consider about, if you say maybe what I can say, the conductivity. So the conductivity is like whenever you have a material, you use a particular material for conductivity, there is a resistance. So when you have this kind of configurations, when I have my cavities made around the molecule, when the cavities are supporting particular vibrations or electronic transition, you can have a faster charge transport. So that is kind of example I can give. So but there are many other examples also available in this particular field, which can show that cavity can advance the material properties. Okay, but how do we do in our lab? I'll just take you a step up. Okay. Yeah, this is my experimental setup. All those things, whatever I told. So now we have, this is kind of microfluidic setup where I have some substrate. Okay, it can be like any substrate depending on the experiment. So that is coated with gold. We coat some 10 nanometer of gold. Then we have a small insulating layer which saves the gold. Then I have small spacer. Okay, the spacer has some empty space. Then I have other substrate. The substrate will have a similar thing. I have substrate and gold. So now I have two gold coated substrates. I am going to sandwich them in between the spacer. So now I have the spacer. On both the sides I have gold coated substrates. So the gold is going to behave as a mirror. Okay, that is going to reflect the light. So once it reflects it, there will be some confined photons inside this spacing. I am going to inject the material in this space. Okay, so this is the space what we are working. It's kind of like tens of microns, like 20 to 30 micron space we have. So we inject the material inside and we do the chemistry whatever we want. So when I have this cavity, you see this is the cavity mode. Whatever I showed in the lines, where the energy cavity modes, what I showed. Sorry. Yeah. So the energy levels, what I was showing here, sorry, yeah, the energy levels, whatever I was showing, it's like kind of whenever there is energy level, you can have transition to different energy levels. So that is what we are seeing by experiment.
To make
Yeah, these are all those energy levels. So these are all cavity modes. So when my molecular transition is matching with any of the cavity mode, that will undergo splitting because they have the hybridization. Well, that's what I showed you in the experimental thing. Yeah. So this is what my molecular transition. I have the cavity mode. I have n number of modes like that. I have many modes. Any of the mode can couple. So then it can form these hybrid states. So then once it forms, we can see experimentally like, okay, I have the hybrid states. The split peaks are formed. So then we have, okay, we make sure that there is a hybridization. Then we go into the chemistry. So this is the point we start and we do what happens to the molecule. Okay, this is the place. This is really pretty new field. This is what we are working. We are a very small group in TAFR Mumbai. We started working from 2022 and we are completely working on this one. So our research is generously funded by DAE and TAFR. So then I would like to thank you for your kind attention.
We take problem. Yeah, we can take some online. So when we shine the light,
Yeah.
do the electrons vibrate
Yeah.
the molecule? And is it possible to discuss amplitude of such vibrations? That's the question.
So when you shine light,
Do the electrons absorb light? And
no, the vibrations are absorbing the light. Yeah.
maybe I think the precursor is,
Yeah.
you could just explain what are polaritons
Yeah.
once again, or what are quasi-particles in
Yeah.
general. Maybe that will help you then answer all these questions. So
Is
that's
it about polariton or?
It's just, but we can discuss. I think polaritons come.
Okay. So
That's essentially what you're doing is polaritonic.
yeah.
matter.
So polariton, I don't have much figures here. Okay, this is the one I can stay.
Without going into dispersion.
Yeah. We know. I'm not going to that. I didn't have that also. Okay, so now okay, so the atoms or molecules are kind of materials, right? That energy transition is the particular energy transition is a fixed one. So for a molecule, if you have a water molecule, water will absorb in a three different units of higher energy to have these vibrations possible. I showed you, right? The water molecules will have different vibrations. So now if I think about cavity mode, the cavity modes are light in nature. So they can disperse. What is the dispersion? Any idea? Yeah, they can disperse. Like kind of depending on the angle where they come, they can disperse. So now when those two are clubbed, okay, now I have a material. Material will have its own material properties like kind of resistance or heating or particular transport behavior. But this light, when you have a light incorporated into a molecule. So now how you imagine these particular energy levels, I have this molecule. This is the only particular homolumo I am saying, only particular transition I am saying, but it has other vibrations, other any transitions also possible in the molecule. But when you have this particular new states possible, now I am bringing new states into the molecule. Okay, now this is a molecule, I have the photon. When we have this kind of hybridization, these two levels are there in the molecule. So when I have those levels in the molecule, now they can behave both light and matter. That is what the quasi particle, what we are saying, they are kind of like very different from either molecule or photon. Okay.
Can I try to simplify this?
Yes, please.
You guys are all from Mumbai, right? Maybe I should go there.
Do you want that?
No, it's okay. Keep it. It'll catch.
Okay.
So you're all from Mumbai. You've been to Dadar station. Okay. So just imagine that you have to walk on Dadar bridge when everybody is, coming the other way. Okay. Now, clearly, the speed at which you walk on an empty street and the speed at which you walk in Dadar bridge is going to be very different. So imagine an electron. An electron, if there is nothing, will go at a certain thing. But imagine an electron in a copper wire or in some material. The electron is going to bang into people. The electron is going to, hit people. In a semiconductor, it might in silicon or something, it might actually be even more slow than it is in copper. Okay. The electron is still an electron. It has its charge, it has something. But if I look at it from far and I see this guy is walking on the other bridge, right? I saw him earlier, he was walking much faster. Now here is the same guy, he's walking much slower. Maybe he just become heavier, right? He's just much larger. So I can, in a material, I can think of an electron in silicon as the same electron, but with a much heavier mass. Okay. So now you have something called the effective mass. How is that coming? It is coming because the collective behavior of all the people around. So collective behavior of many different particles can give you a kind of, in a way it's the same electron, but it's a quasi particle. A quasi particle means it's something whose behavior is controlled by other people in its vicinity. Okay. So here, of course, I've just mixed electrons with other, there are atoms and whatever else around. I can do the same thing in a crystal. All the atoms are vibrating about their position, right? And heat transfer or anything depends on how these things vibrate. Okay. Now, just like I said that there was in light, now by now you've heard this so many times from school that light is both a particle and a wave, etc. Right? Nobody told you sound was a particle and a wave. But suppose I had to tell you sound was a particle and a wave, sound waves. But now I can think of, if I have vibrations in these materials, I can think of as if there are some particles that are moving of sound. These are called phonons. Okay. Phonons are kind of quasi-particles based on vibrations of lattices. These lattices which are these things are in. Now here again, I'm just coupling just vibrations of lattice. Now I can couple different materials. In this case, if I try and couple light, on one side there is light, on other side there are energy levels of something, of a molecule. I can, and these happen, you'll never see this in one molecule. You will see this if there is a lot of molecules, a lot of light, they can couple together and bring you and sort of it's there, the molecules are there, the light is there, they're doing whatever they're doing. For our understanding, it's easier to think of it. If I think of it, the light and the molecules have mixed up to create a new kind of particle, which is this polariton. Right? And the energies of these polaritons are such that they have, whatever the energy level is a little bit, there are two states, one
Separate.
slightly above, one slightly below, and their behavior as in this half photonic and half electronic, half like light, and mathematically they behave half. If I try to analyze how I will write things, partly they behave as if these are light-like particles, partly they behave as if these are just collective modes of a system where there is light and there are particles, and I'm mixing the light and the particles and trying to write it in a way which makes life simple for me. So, for example, I work in semiconductors, right? Now, what happens in semiconductors is that often you have all these electrons going on. Dadar bridge. Okay, just this Dadar bridge is a fantastic example. Explains all of physics. Okay, so now just imagine that everybody is going in one direction. Okay, now there is this one guy who is trying to come the other way. Okay, or there is one guy who's now technically, if I had to write equations for something, I had to write an equation for everybody out there. But I'm interested only in this one guy who's coming. So I can think of one guy as like an anti, he's a hole that's moving. Instead of all the people moving this way, there's one empty thing that is, because the guy keeps shifting this. I won't track all the people to make life convenient for me. I will track this one hole that is moving in the other direction. So sometimes you can just say that just to keep the mathematics simple, instead of taking into account that otherwise I will have to, in a real material, there are 10 to the 23, what he said, Avogadro's number of particles. I can't take into account that many particles. I'll take into account these few guys who are missing and track those missing particles. It's easier for me to track 5 missing particles than 10 to the 23 minus 5, that many particles. So these are just mathematical tricks you use. And one of the most powerful things is to say that I can mix two kinds of things. In this case, light and transitions. And get you these states, polaritonic states. And the fact is, once you put these things, remember these mirrors are not like one mirror there and one mirror here. They are very closely spaced. That is when the energy spacings, the mirror supports. See, the point is, if there is light between the mirrors, the light has to be absorbed at this end and that end. I mean, it has to be zero whenever it touches the mirror, right? The field can be maximum only in the middle. It can have other zeros in the middle. That's what he showed by the different. Yeah. So it's like a string, a fundamental mode, a harmonic mode, whatever else, right? You have these modes. Now these modes, if I make the string, the cavity larger or a string lower, the frequency will go down. If I make it small, the frequency goes up, right? At some point, these frequencies match these frequencies that the atoms are giving me. Then I can mix and have fun with them. And that allows you to control properties, control reactions. Then you can do fun stuff, which is lab does. Which is not even talked about.
Yeah. True.
Anyway, you can tell us some fun stuff that can happen in your lab.
Yeah.
Also, and then we can take some more questions.
Yes.
Yeah. So, firstly, the fun stuff.
In the
lab.
So, let me ask you, why are people interested? We've been doing reactions, we've been doing something.
Yeah.
Why are people interested in harnessing polaritons?
Okay. So,
how do you, you're saying that this is such a small thing.
Yeah.
Are these stable for a very long time?
yes, that's what we showed in the experimental thing. So these spacers are stable. These are all like polymeric spacers. They are stable. It's very stable, like kind of like PET, or even we can use alumina, glass. So they are very stable. So there's no problem. So now, so I'll tell you, it's like kind of a small story where it behaved, it started or something way. So surface plasma, okay. So once one of my postdoc professor, so he wanted to study the molecules inside metal mirrors, like whatever I'm saying here, the gold, he wanted to take a metal hole and he want to put the molecule inside the hole. Okay. Then he was a scientist in Japan. So now he told that scientific officer to make this kind of structures he want to study. So in Japan, scientists are not doing this kind of thing. Only the assistants will do. They will only do experiments. So this Japanese person, he didn't understand what he was asking. So what he did, he made thousands of holes on a gold film. So he wanted one big hole, then this guy made multiples of holes on a gold film. So then my professor took it to microscope and he said, oh, this is useless. So I cannot use this particular system at all. Then he was seeing there was some intensity of lights are really high in that particular microscopic image. Then they found, okay, there are something called surface plasmon modes, which are emerging from this kind of surface. It means I can have only particular frequencies coming out of the surface, not all the light. When I'm sending some light through the holes are very tiny. They are like 100 nanometer or 200 nanometer. They are, due to diffraction limit, none of the light will pass through. But he could see some of the lights are coming out of the nanoarrays. So then he found that depending on how the holes are arranged, okay, the frequency of light comes out of the film was different. So I give some 500 nanometer light, blue light, through the holes. I don't get 500, I get somewhere around 600 nanometer light. So the holes have some filtering effect to give some only particular frequency. So that he had a control. I can choose the distance between the holes to tune the frequency. Then he had something like, okay, this is kind of confining light and giving only particular frequencies out. Then they what did? Then they thought about this kind of experiments. Okay, I will have a molecule just next to this particular surface. I'll see what happens to that. Then they figured out this kind of strong coupling. Then they started having chemistry. The chemistry was started some 10 years back. It was like, it was kind of curiosity. They didn't start with the kind of understanding like, okay, we'll see that this is what we are going to do. So they just wanted to see what happens, we will see. Because now I just have an analogy here. It is nothing to do with a molecular thing. So now you have an environment. Okay, everybody is having very sensitive to the environment, right? You go to some environment, the environment makes you to feel different. Okay, some place you feel very positive, some place you feel very negative. Sometimes you will see that collectively when you have same kind of what the environment which is matching with your particular wavelength, you feel positive. Okay, you feel kind of like, okay, I have more energy. So similar analogy you can think of any molecule when it is in the environment which has supporting wavelengths or frequencies, the molecule behave differently. But it is not only the environment. Okay, the environment should hybridize with its particular molecule. Once it happens, you have all this fun thing. But now you see like kind of this emerges a new field. The people across the globe are kind of working to understand what is happening. Still we don't know what is happening. We are saying like, okay, these are all things being observed, but still we don't know what is happening to the system or how it is behaving in this way. How to see that in a very nice way, that and all is still under progress. Okay, still it's happening, but I don't know what fun I have in this one.
Like you make mistakes.
Yeah, we make mistakes, definitely.
That's the fun.
What's your interest?
By the
So-
way, I don't know if you heard him, but I think he started now saying that the surface plasmon that.
Yeah.
Plasmons are another example.
Another example, yeah.
So metals have electrons just sloshing around everywhere. Right? Electrons are free in a metal, they can just go wherever they want. So this free electrons sloshing about in a metal is like a plasma. And again, this plasma has certain frequencies. Right? And near the surface, you can often have oscillations of these, things which behave as if there are some particles of this.
Yes.
It's easier to understand them in terms of these are plasma. And often, if you see very thin metal films, they have certain color. That's because of this, the way the light is interacting with this. So light is interacting with this sloshing around
Electrons.
Easier to think of it as a plasma.
So now you have to think of.
Plasmonics about say 20 years back changed a lot of ways we could sense, we could increase it, because near a metal surface things are very, very, you can couple to this thing, then you can use both the electrons and the light together, and now polaritrons allow you to do
Yes. So it's kind of similar phenomenon like surface plasmons, but this is like there you have to have some particular structure of metals, and here we can use even optical resonators. So my interest in this field is like mostly what we do, we couple the molecular vibrations. So we all know that chemistry is mostly about vibrations. So when you want to do some synthesis or you want to harm transformation from a molecule A to molecule B, I have to break a bond and I have to make a new bond. Okay, so breaking and making the bonds are the importance of chemistry. So now to break a bond, I have to increase the vibration. So how I can break it, I have to think about the molecule is vibrating, an atom is vibrating, two atoms are vibrating together. Now I have to think about this particular vibration. Now I couple this particular vibration to the cavity mode, and I can see whether I enhance that rate of fission or whether I can perturb it. That is what my interest is. Yeah. Clear thing?
Can you keep only small molecules or can you keep proteins?
We
Somebody was
can
thinking
put
about
any
proteins.
molecules. We can put proteins also.
You can put proteins.
We can. Even proteins, it will be like kind of in nanometer in size, right? So the kind of space we are working is in microns. So we can put proteins.
You would like to look at simpler molecules.
Simpler molecules to understand the mechanism. So if you think about protein, it will have a giant size. Yeah, it's complex.
How close can you go? Keep going further and further.
We can go in nanometers, like kind of tens of nanometer we can go. But kind of energy what we are dealing now, at least we require, if you think about the visible region, that itself it requires some kind of 400 to 500 nanometer thickness. But if we go below, but we are not much interested in those things.
Okay, you guys have come here, you'll get chai, something. For the online audience, I don't see any more questions. We will end it, but just to announce that from now on, the next 3 chai and wise, you can hear it as well, are going to be about the Nobel Prizes in Science for this year. So 2 weeks from now, we will look at the Nobel Prize in Chemistry,
In biology.
which is
Jyotsna.
which is about these new kind of structures called metal organic frameworks. Moving from that, November has a 5th Sunday, so that will be a session on the Nobel Prize in Physiology or Medicine, which is on the peripheral immune system. And given that it's a Nobel Prize talk, it will not be online only. We're actually trying to have a hybrid version of it, so it will be in person somewhere. And then a month from now at Prithvi, we will have the Nobel Prize in Physics. That we have kept as a separate, we've kept essentially all the sessions separate because this year's Nobel Prize in Physics is rather unique because the one of our TIFR faculty members, his boss, his advisor got the Nobel Prize, was one of the recipients, and he's worked with all the 3 of them. So so since he knows them personally and something, we decided let's have a full session on it, and we have a person who actually knows and has done that
Correct.
experiment. So that's going to be the next session, which will be in the theater. So those are the next 3 chai and wise coming up. You can now on this note, we will end the live stream. Of course, you can send us questions on outreach@tfr.rs.in. And now we have enough time here. We can have chai and come back and get more questions and comments and whatever else. Okay. So once you're done with you can go back to your first time.
Yeah.
So should we break for a cup of chai?